Okay, so I'm going to try to reinstate the mental state that I was in as of last class. And we were talking about smart water. And we said that smart water, they claim to have a mean of 700 milliliters. And we might be interested in seeing whether or not this is true, right? And we would expect, due to just random variations in the equipment, for some bottles to get filled up more or less. So we're not going to say, oh yeah, the company's a liar if we happen to find one bottle with like 680 milliliters. That's not that big of a deal. That happened, or that might happen. Actually, I'd be surprised if their machinery was that far off. But anyway, what should happen is that on average, we have 700 milliliters. Now, if we have like smart water, are there any calories in smart water, or caffeine or anything, or is it just water?
Zero calories. Oh, there's electrolytes.
Electrolytes. All right. Let's talk about Coca-Cola or something else, something with calories. People might want to know how much they're consuming. So if we had a 700 milliliter bottle cans thing of Coke, we might not want to have too little because we're paying for those calories. We want to get them, but we also might not want to have too much because we're trying to regulate our caloric intake, right? So we would expect there to be some variations around 700. If we had access to the entire population, we might find a distribution like that. So imagine that this is like a histogram with very fine little bars. It's possible the distribution might look a little bit differently. It could be something like that, where it's a bit skewed to the right. But ultimately, that doesn't matter if on average we find there to be 700 milliliters of Coke. Now, because we know about the central limit theorem, this is a beautiful thing, because it means that we don't have to necessarily make the assumption that the underlying population is normally distributed. The distribution, it could be binomial, right? So half of the Cokes are coming out with 690, and half of them are coming out with 710, but still on average we're getting that. And we know, because of the central limit theorem, if we take a large enough sample, that the distribution of the sample means will be normally distributed. So imagine that we didn't have access to this underlying population. I mean, we know that it's supposed to be 700 milliliters, but we don't know what the variance or the standard deviation is. Maybe it's one of Coca-Cola's trade secrets, and they're not going to let that information out. So how do we figure out what the variance of that population probably is? We take a, not a survey, yeah, we take a sample, right? We take a sample. And then we calculate the unbiased estimate of the variance from that sample, right? Because this estimates what the variance of the population would be. Now, do you guys know about the null and alternative hypotheses? Because these come into play here. So what are the difference between the null and the alternative hypotheses?
Are you asking me directly?
I was asking it of anyone who was nodding their head, but yes, you.
It's like, the null hypothesis is like, usually, it depends on if it's like a one-way or two-way.
Certainly.
But it's, your alternative hypothesis, I'm just going to start with the alternative hypothesis.
Great.
The alternative hypothesis is what you're actually asking and what you think might be proven by your...
Not proven,
Yeah.
but what you might think might
Be
have
demonstrated.
sufficient evidence
Yeah,
to make a claim of truth about it.
Yes, by your test. And the null hypothesis would be if that's not true.
If that's not the case.
If that's not the case. Basically.
So if we're talking about 700 milliliter things of Coca-Cola, what would the null hypothesis be? Or what would the alternative be? What?
The null hypothesis would be all Coca-Colas are 700 milliliters.
Right. Or maybe not all of them, but the mean. The mean bottle of the 700, with the 700 milliliter labels, the mean for that is 700 milliliters, right? So that's the null hypothesis. It's the starting point. And this gives us a parameter. This is important because in order to, create a model, we need to know what those parameters are, or we need to be able to estimate them. So we look on the label and we see 700. So we say, okay, we're going to go with what Coca-Cola says. Because it would be silly to go and try to sue them for either stealing our money by providing us too little Coca-Cola, or for making us fat by giving us too much Coca-Cola, unless we've got sufficient evidence to make either one of those claims, right? So the null hypothesis is basically the, oh, my brain just farted. Null hypothesis, when it comes to issues like this, is basically a statement about the status quo. So in other situations, we might not be interested in a single mean, but we might be interested in differences between means. Is there a difference between murderers and non-murderers when it comes to aggressiveness as measured in some way? Right? What would the null hypothesis be in that situation? They don't. That's exactly right. So the null hypothesis there would be saying that the two means are the same, right? So what's the parameter for that? Well, if the two means are the same, then that means there's no difference between the means. So we'd say that there's a difference of 0 between the means. So in most cases, the null hypothesis is a statement of no effect. Studying doesn't help you get better grades. Drinking coffee does not increase your alertness. Things like that. In some situations, we'll have null hypotheses that make a specific non-zero or non-null prediction based on claims that other people are making. So we draw a whole bunch of observations from Coca-Cola, and we see that our observations, the mean of that is 710. Now, there's going to be some variability, right? Some are going to have a little more, some are going to have a little bit less. So if we were to create a standard normal, let me draw this up higher so I can center better. There we go. So we find a distribution like this, okay? We observed some mean, 710. We observed some variability. Knowing what the variability is, we can just plug that information into a calculator or a computer program like R and generate what the normal curve would be with that mean and that standard deviation. Now, remember, this is an estimate. The standard deviation that we come up with here, the variance that we come up here, is actually an estimate of the variance of the true mean, which Coca-Cola says is 700 milliliters. So you can imagine that maybe our mean was off, because means are going to be off sometimes, right? But even if the mean is off, since this is an unbiased estimate of the variance, we could create that distribution around the mean that we believe is the case under the null hypothesis. Does that make sense? So basically, we would want to draw the same distribution like this, centered on 700, sorry. So when are we going to say, aha, Coke is ripping us off, or I guess in this case, not ripping us off, but Coke, they're giving us too many calories. We need to sue them to pay for medical bills, whatever. Yeah?
When the probability of it being a coincidence is less than 0.05.
So when the probability of it being a coincidence is less than 0.05. Saying that slightly differently, we're going to say when the probability that observing a mean of 710 or a mean that is as or more extreme than that is less than 0.05. Right? So that would probably be in this region right here. It's sort of hard for me to estimate exactly what the probability would be, and the same thing on the other side. Right? So if this was the point where P is less than or equal to 0.05, and we actually observe this, what do? We reject the null hypothesis. That's one claim. So there are two possibilities. One, we reject the null hypothesis. The second is accept.
Well, that's just the other.
I'm going to use different terminology.
Yeah.
Fail to reject. Yeah, I like that much better. We're going to either reject the null hypothesis or fail to reject the null hypothesis. So, fail to reject. Can you imagine if people dated like this? Hey, baby, want to go out? No, I reject you. Yeah, I failed to reject you. Okay, so we had some people saying that we should reject the null hypothesis. How many of you say we should reject the null hypothesis here?
Did you say P is less?
5, 6. How many people say that we should fail to reject the null hypothesis?
Did you say that?
So we observed 710, and this is the region here. We had it like, I don't know, 712.
Okay.
How many people say fail to reject? Nobody?
There are only 6 people.
Oh, I'm glad we're doing this. Because everyone who voted was wrong. And everyone who didn't vote either didn't know or didn't have the confidence, so we should cover this. So, maybe it's confusing because we drew 2 overlapping distributions. So boom, here's it. Oh, it's so much easier if I draw that first. So 700. 700 is the mean. It has some variance that we estimated, and we can figure out what these rejection regions are. And the idea is, if we observe any mean in here, or any mean in here, we're going to fail to reject. And if we observe any mean in there, all the way out to infinity, and negative infinity, we will reject. This makes sense. If we're flipping a coin 100 times and we want to see if it's fair, if we get 50 heads out of 100 flips, well, that's like right here. That's really likely. We would expect a lot of times to get 50, right? If we got 49, well, that's not as likely as 50, but it's still pretty dang likely. As we get more and more and more heads, or fewer and fewer and fewer heads, it becomes less and less likely. So if we observed 100 heads out of 100 flips, that's way over here. It's highly unlikely.
I think I misunderstood you, which is why I was asking if P is less than 25. I thought you were talking about the specific white region there, not the actual 700.
Oh, so
Yeah,
if
I
it was in
thought you were talking about the 712. Would that be the fail, or would that be the rejection?
Yeah.
Well, then my bad. If I said it incorrectly, then it's completely my fault, and I'll take your hate mail or whatever.
So you're talking about the 700?
Yeah, I was talking about the 710,
Yes.
right? Because I said that that's what we observed, and if this is the rejection region, what should we do? But if you're thinking about, well, if we observe something over here, then you're exactly right, right? So everything that's pretty close to the mean, relative to the variability, we're going to fail to reject the mean, which is evidence that the null hypothesis at this point in time seems to be the best hypothesis, right? But if we observe something that we wouldn't expect because it's so unlikely, given how the data are distributed, or given how the sampling of the mean should be distributed, then we're going to say, whoa, 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 whoa. Like 80 heads out of 100 flips? It's almost impossible unless the coin is biased, or the flipper is biased, or something is biased. So we're going to reject the null hypothesis that everything's fair, everything's on the up and up in that situation, right? It could just be a mistake. It could be that there really is no bias and you just happen to get lucky. And that's where thinking about both of these distributions comes into play. So if we have some value here that cuts off, p is less than 0.05, then everything on this side, any means, we will reject. I don't really want to get into the one versus two-tailed thing. So if you don't understand, just go with it. But let's say all of our probability is on one side and everything over here we will fail to reject. So sometimes the evidence will come out just due to chance in a way that will lead us to reject. Sometimes, despite real differences, things will come out in a way that will lead us to fail to reject. Now, if you notice these two distributions, they fall in different places relative to this line. So this distribution around what we thought should be the true mean based on what Coca-Cola was telling us. Notice this only has a little bit of its area beyond this, right? There's very little of that distribution beyond 0.05. In fact, there should only be 0.05 of that distribution beyond that point, right? But how much of this distribution, the one that we created with the value that we actually obtained or observed, how much of this goes beyond? A little less than half. We can also say a whole lot more, right? Now imagine if we observe different things. So what if we observe something like this? So this is the null hypothesis, and this is what we actually observed, 727. Would we reject or fail to reject? We would reject, right? Because this is way beyond this point over here. Way beyond. How much of this distribution is beyond this line? Almost all of it, right? So earlier we talked about an outcomes matrix. And capital T, truth, effect, no effect, and our conclusion based on stats of an effect or no effect. And if we are in this quadrant, this is an error. And if we are in this quadrant, this is also an error. So in this situation, this would be like there's no effect. There really is no effect, right? So it would be like observing something over here that was just due to chance. What can we do to control how often we make these types of errors? These are called our, does anyone remember, is it type 1 or 2? Type 1 or our alpha error. What can we do to control our alpha error?
Larger sample.
Larger sample size? Is that going to do it?
Well, yeah.
If we had a sample of 10 and we said our alpha is going to be at 0.05, that means that 5% of the time we're going to be wrong by setting alpha like that, right? If we had a sample of 1 million and we set alpha at 0.05, what would that mean? 5% of the time, when the null hypothesis really is true, we're still going to reject it. So we're not going to do anything by increasing the sample size. So what can we do?
Alter the p-value? Or would that be the...
Well, the p-value is going to be the p-value.
Oh, I mean, like, maybe instead of like the 0.05, go to like 0.1?
Huh. We could change the alpha.
Yeah.
So if we went from 0.05 to 0.1, would that shift it this way or this way? To the right or to the left?
Do you want 0.1 or
0.1. She said 0.1, so we're going to work with that.
Well, that would go to the left.
That would go to the left. So if this is equal to a p-value of less than or equal to 0.1, are we going to make more or fewer type 1 errors? We're going to make more type 1 errors, right? Because we just said instead of having an error 5% of the times when the null hypothesis really is true, we're okay with it having an error 10% of the times. But I think what you were trying to say is make it 0.01, right? Which would shift it down here, which would have what effect? It would have exactly the effect maybe that we want. It would decrease the type 1 alpha error. The type 1 alpha error is completely dependent on alpha. So if type 1 error represents having an observation that's out here that was just due to chance, what does a beta or a type 2 error represent? He said. So instead of having an observation over there, it would be having an observation in here. Right? When? When the null hypothesis is true or when the alternative hypothesis is true? When the alternative hypothesis is true. So this would mean like we observed a mean right here and the true distribution is really shaped like this. Sorry, it should go up to the same height. So the true distribution is like that. However, since almost all of this distribution fits within this area, what's going to happen? We are going to make type 2 errors all the time when we have just little effect sizes. It's a small effect. So what can we do to decrease beta errors? Let's say decrease alpha errors. You can decrease alpha. And to decrease beta errors, what can we do? There's several things. If you hit one of them, has to do with alpha. Increased alpha, that's exactly right, right? If we increased alpha, so the cutoff point was here, now more of this distribution would be on that side, which means that we're going to make we're going to incorrectly fail to reject the null more often. Wait, less often, yes. Does that make sense? So if we increase alpha, for our alternative distribution, it just pushes more of it into this side. It's also going to push more of the null distribution to that side as well. But one way we can decrease the amount of times that we're going to make a type 2 or a beta error is by increasing alpha. What are some other ways? What was the one way I suggested? No, you can't do that to change alpha errors. Sample sizes. Can sample sizes affect beta errors? Yes, he's nodding. You're absolutely right. Good job. What do we need to do? Do we need to increase the sample size or decrease the sample size? Increase. He's absolutely right. Increase sample size. I'm just going to say n. Increase n. Why is that going to work?
Increases the chances so that they're proving that it was just a...
Not proving.
Or showing that it was just a chance.
How?
Because if you have more sample, it will put it into the right position, so you have more in that.
But, okay, so
What
hold
the
on.
correct means.
So let's say the null is 700, and we observe 710. Oh shoot, I should have drawn the distributions first. And we did it with some sample size. Sorry, those should be equally tall and equally shaped. So let's say that this is the real truth. The real truth is 710, it's not 700, and we got something very close like that. And let's say with a larger sample also, we're going to get something very close to that, right? So it's not that it's going to push something out more or bring it in more. What's going to happen?
The steep.
Not necessarily, you're so close. Yeah, it's not going to change the standard deviation, right? Because the standard deviation that we're estimating, it's unbiased, so that should be on average what it is in the population. However, it's not the standard deviation that we care about so much in running these tests, it's the standard error of the mean. And what happens as the sample size increases? It's not, it's. So remember, we've got the binomial distribution, we've got half of people over here and half of people over here, and then all of a sudden we increase the sample size, and now only a quarter of the people were over here, and a quarter of the people were over here, and, is that right, a quarter and a quarter? And half of the people were right there in the middle, right? We took a little bit more, and now only an eighth of the people are over here, and an eighth are over here, and we've got more in here. So as we increase that, remember we said that the standard error of the mean is equal to the unbiased estimate, or the unbiased estimate of the square root of the variance all over the square root of n, right? So as the sample size gets really, really big, the standard error of the means gets sucked in. So what would happen if we increase the sample size is the distributions would look more like that. It'd actually go up higher. There we go. Such a bad far. Now what happens? Well, okay, let's say we're not touching alpha at all, and we're going to say 0.05, and it's over here. This is the point now. Before the point was over here, right? But by taking a larger sample, what happened? Our standard error of the mean got much smaller, which means that this p-value gets much closer to the value predicted by the null hypothesis, which means that if the real difference is 710, what happens? A lot more of this distribution actually is outside, actually outside of that cutoff. This is a good thing. This is one reason it's a good idea to take larger samples. If you don't know what the distribution looks like, how many of you guys have had a stats and they say like you should take a sample size of blank? If you don't take the sample size of blank, then you should do something different. What's that blank? Who's taking stats? Okay, or 30, does 30 ring a bell? 30, yeah, so 30 is the point where like the binomial basically is or the normal is a very good estimation of the binomial distribution with that size sample. So if we take a sample that size, the central limit theorem comes in, but if we take a sample that's even larger, we're going to suck in that standard error of the mean, which is going to end up separating these two distributions from one another more. So what most of our statistics are doing are comparing like what we expect under the null hypothesis. This is what we expect compared to what we observed. Right? And there's variations between what we expect and what we actually observe. Right? So this would be the effect of something. Maybe these are two different groups. One, we've given 700 milligrams of caffeine, and another we've given 710 milligrams of caffeine. That doesn't, sorry, just erase that. This is like a frequency histogram type graph, not something else. So ignore that. But the point is that what we're doing is we're comparing the deviation between what we expect and what we observe. And we are comparing those deviations between our expectations and our observations with the deviations that we would expect given our sample size, given the null hypothesis. So those deviations that we expect, those are just deviations due to error as opposed to deviations due to an effect. the effect of having maybe a Coke bottle filler that's under just a little too much pressure and is getting too much Coke in it, right? So that's an effect. And the way that we identify the effects is by comparing the effects, the variability in the effect, with the variability in here, the variability of our error. So we can decrease beta errors by increasing alpha, by increasing n, anything else. Let's say I want to see if saying boo to somebody scares them. Okay? And the null hypothesis would be what?
Mostly.
The null hypothesis?
Unnecessary.
Right. So the null hypothesis would be like saying boo to someone, it doesn't affect them at all, right? Let's say I want to measure how scared they are by measuring their heart rate, okay? So I'm going to take a sample of a whole bunch of people and I'm going to go up behind them and I'm going to go, boo. So I've got my sample size, whatever it is, and I've got some variance, whatever that is, and that's going to create some distribution under the null and some distribution centered around the actual value that I observed, right? So if the cutoff is here, we're going to make a beta error this number of times, the number represented by that area. So we're going to be making a 1. So without changing alpha, and without changing the sample size, what else could I do to see if saying boo affected people? And have a better chance of not making that type of an error? It has to do with effect size. So this is some effect, right? There's a size of that effect. What can I do to make that effect instead be that big? Boom! Would we predict any difference? Did that scare you?
I predicted it to be pretty scared.
So would it be like the salience of it, or?
So we can make our manipulation more salient, right? We do something to see if there's a bigger effect. Let's see if caffeine affects how people, act. I'm going to give you no caffeine, and does anyone have a caffeinated beverage with them?
I just.
Oh, great. Let's see how much caffeine there is. I really don't know. They don't tell you?
It's really hard to find if they do. They see your lunch.
Why isn't that important to know?
It should be, but I have problems.
Okay, well, so if 100 milligrams is the normal dose for one of those things, let's say I had no milligrams and 1 milligram. Is there going to be a big difference that we see? Probably not. When I first got to college, I thought oh, I'm in college now. In college, people drink coffee, and I didn't drink any coffee growing up. But I started on my very first morning in college. So I brewed myself a pot, and I drank the whole thing. And what happened? No, I didn't wake up in the hospital. Yeah, my stomach was like, what is going on? And then I'm all tense, and I'm sweating like a pig. And all of these effects of the caffeine, right? Why is that? It's because I didn't have this tiny little manipulation where I went from 0 to 1. I went from 0 to 1,000 milligrams of caffeine, right? So we can increase or decrease our beta errors by increasing alpha, increasing n, and do we decrease or increase effect size? Increase. And we can do this by making a more effective manipulation. Does that make sense? So out of all of the ways that we can decrease beta errors, which would be good things, which would be bad things?
Increasing alpha would be a bad thing.
Increasing alpha would be a bad thing. Why?
Because it can skew your data to how you want it, and it's one of the faults of the thing we talked about before.
So you can skew your data the way you want it. It's not going to skew your data. Your data are going to be what the data are.
About the results that you got.
Yeah, it's going to change the results that you find. It's going to turn something that previously was beneath that or above that p-value to something that's beneath that p-value. So this means that when we decrease our type beta errors by increasing alpha, we are trading off one thing for another. And this isn't good. I mean, if we really have a good reason for doing that, we could, but we might as well leave alpha at the traditional level, or even make it more stringent than the traditional alpha, so that way, we're not wrong 20% of the time, or 5% of the time when there's no effect, right? So increasing n and increasing the effect size are both going to work in our advantage. We can't always increase the effect size, right? Sometimes things are what they are. I want to see if there's a difference in how much people like, I don't know, one brand of caffeinated beverage versus another brand, and I'm interested in the caffeine amounts. Well, those two amounts are set based on the manufacturers, right? So for some questions, I'm not going to be able to make that manipulation. I can manipulate people and say, okay, you drink A and you drink B and you drink A and you drink B, right? But I can't manipulate the caffeine that's in those A and B. So sometimes you can't do the manipulation to increase the effect size, but we can increase it. So increasing N is one of the best ways to get more. If this area, let's try this again. If this area represents probability of making a beta error, what does all this represent? It's going to be the probability of what? Do I have it up here? No. Probability of one of these with a little more language. So this represents, are we going to reject or fail to reject over here? We're going to reject. So the probability of something rejecting the null. Are we correctly or incorrectly rejecting the null here? So that is up here, right? There is an effect, and we say that there's an effect. We call this a hit. Confusing you guys by saying correctly rejecting. That's the probability of correctly rejecting the null. And this has a special name for it. One word to describe the probability to correctly reject the null. It starts with P. I think Homer Simpson took this name in one of the episodes. Called himself Max something. Power. That probability is power. Power is the probability that we will reject the null when the null is false. We want power. One of the things that a lot of people don't do is they don't do a power analysis before they run an experiment. They have some idea about how big the effect is that they might like to see, but then they just go out and they collect some data. And if you just run out and collect some data, but you haven't done a power analysis to see how many people you need to obtain some certain amount of power, right? Because we can do that, because we know as we take more people, we know how the distribution shape will change. And then we can figure out exactly how many people we need to get. So there is this much, or a certain amount of stuff in that region. So, on power analyses. What time is it? What day is it? Friday? Okay. Yes?
Okay, so by increasing the sample size, it's a good thing to get rid of the beta error. But isn't
And it helps decrease the probability of making a beta error. Yes.
Isn't it a bad thing when we go back to the file drawer effect and the publication bias and those kind of problems? That is not one of the problems by just increasing your sample size to get the specific results that you want?
Huh, okay. I see where you're going, and let me see if I can answer this. So one thing, by increasing the sample size, you increase your power. And one of the things that you want to do is make sure that you have enough power to detect an effect if it's there, right? So one of the reasons that experiments don't get published when they don't find anything is because it's possible that really the truth is there was nothing there, right? And it was just due to chance. And unless you do a power analysis to see how much power you had or what probability you had to observe an effect, if that effect was real, it's possible that you just didn't have enough. So, I mean, imagine something where you have just a slight difference in ability. Let's say males and females in mathematics ability, and let's say that women are better than men on average. Well, it's possible that these distributions look like this, right? And so almost never are you going to observe this mean difference as being significant. Unless what? Unless you take huge sample sizes to make these things much steeper, right? So it's possible that there is a real effect. And unless you make your manipulation powerful enough or your design powerful enough by increasing the sample size, you're never going to detect it. Now this leads to one problem, because some people say, well, you know, if you increase your sample size enough, you're going to find a statistically significant difference, because you're never going to find it where they exactly match up. Yes, but no. You're comparing the difference in what you observe with what you expect with the variations that you should expect, given the variations in your sample. So we're sort of taking care of that. Now, where the problem comes in is when you say, like, okay, I want to collect 16 people, data from 16 people, and I'm going to look at the data. And I look at the data and I see that P is equal to 0.06. So you're like, shucks. I wanted it to be 0.05. That's not 0.05. So what happens? Okay, well, I'm going to add another person. All right, so that changes it. If you add one more person, this value can go up or down depending on how that person's data are. So maybe this goes up to 0.07 something, or maybe higher. You're like, well, you know, let's add a couple more people. So you add another person, and it goes down to 0.054. You're like, well, shoot, we can round. No, sorry. So you add a couple more people, and you find, think about the coin flips. The probability of getting a heads on one trial is 0.5. Probability of getting a heads on the second trial is 0.5. To figure out the probability that we're going to get two of those in a row, we're going to have 0.5 times 0.5, right? So there's something similar going on here. that very first time we run the test, we're saying, okay, we're going to be wrong 5% of the time. But then we run an additional test and saying that we're going to be wrong 5% of the time here. So you take a whole bunch of these tests where I could be wrong here, I could be wrong here, I could be wrong here, I could be wrong here. You're massively increasing the probability that you're going to be wrong. Does that make sense? So what you want to do is run the power analysis first to figure out how many people you need to observe a particular effect size. And then say, I need 38 people. And then you go and get 38 people and you stop there. So that way you aren't running multiple tests and capitalizing just on chance. Oh, I got the right person that next turn, hallelujah. Does that make sense?
Yeah.
So it's not that increasing size by itself is wrong. I love increasing size. However, it's the conditions under which you do it. If you increase the size and say, let's be sure that we've got something here. I know you want to run 16, but it's really easy to find participants at this time of the year. Let's run 32. Let's double our sample size. Rah! Great. If you collect 16 and you look at your data, you take a peek and you're like, we need to collect some more, that's bad. Then you're capitalizing on chance.
Okay.
Does that make sense?
Yeah.
Anything else? Are there any questions? Okay, we'll come here.